We are going to start discussing now one of the most important applications of derivatives, optimization. Here, the point is, when we want to optimize, what we are trying is to make something as big as possible or as small as possible, a maximum or a minimum. And we have seen that derivatives allow us to find the maximum or the minimum of functions. Okay, so that's the connecting point between optimization and derivatives. So let's start with an example. Here we want to find two numbers whose difference is 100 and whose product is as small as possible. So in a problem like this, the first thing we need to do is to decide on the variables that are important. In this case, we have two numbers, so clearly we need to name those two numbers. So let's say x and y are the two numbers. Okay. And the condition that we are given is that the difference of the two numbers must be 100. So let's say y minus x equal 100. I could do x minus y, it doesn't matter, okay? But let's do y minus x. And then what I want is the product as small as possible. Okay, so here, if we try to do this by brute force, we could start sampling, trying different pairs, and keep always the smallest, the pairs that will give the smallest product so far. But the problem of this approach is that we will never finish, right? Because even if after a while there is some pair that looks like that should be it, that it's beating like every other pair that you try, how can you be sure that's the one and you are not missing some other one? Just by chance, you will never know because there are infinitely many choices, right? So that's one thing that this method we are going to see is also very useful, because it allows to know what are, when you find an optimal point, that's it. Okay, you know that's it, and there are no others. Or if there are others, you know all the possibilities. Okay, anyway. So here, to be able to apply calculus, we need one function in one variable. So here, what we notice is that the restriction y minus x is telling me that y equals x plus 100. Okay, so then I can combine the two things and say, well, I want to minimize the function f of x equals x times x plus 100. Okay, that is x squared plus 100x. And then this is very easy because I only need to take the derivative, 2x plus 100, make it equal to 0. And then I find that x needs to be negative 50. Okay, and then if I do a sign chart here, and I have the negative 50 here, so I'm going to realize x, the function is x times x plus 100. So if I'm on the left of negative 50, x is going to be negative, and x plus 100 is going to be, sorry, I'm looking at the function, but I should be looking at the derivative, my bad. So 2x plus 100, if I'm on the left of negative 50, okay, 2x is going to be, at best, negative 100, but it could be smaller than that. Okay, so this f prime is going to be negative, and on the right is going to be positive. Okay, so f is decreasing, then F is increasing. Okay, and that means that 50 is a local minimum. Okay, actually, in fact, this is a parabola. Okay, if we look at it, is x times x plus 100, so that means it has two roots, negative 100 and 0. So it will look something like this. Oops. Something like this. And then back up. So it will have a minimum, and that is going to be an absolute minimum, actually. Okay. And that's it. So the two numbers. So if one number is x equal negative 50, then what is the other number? The other number is going to be negative 50 plus 100, so it's going to be 50. And with this, we have the two numbers that give the product as small as possible. And the product is going to be negative 2500.